So hello everyone. Good afternoon. Good afternoon, students. Am I visible and audible to all of you? Yes. Okay. Okay, then let's start the class today. So we are discussing the P block elements, right? Group 13 and group 14. So in the last class, we have discussed the introductory part of group 13 and some of the general properties, that is physical properties, and some general properties of group 13 and its elements, right? Now I'll ask you one question from that. So let's start with the question from the previous class. So why aluminium does not react with concentrated nitric acid? So in one of the point we have discussed, no, that aluminium does not react with concentrated nitric acid. Can anyone guess the answer for this? Why it doesn't get react with the nitric acid? Any idea for anyone? Why aluminium does not react with concentrated nitric acid? Concentrated nitric acid is HNO3, right? So I told you that aluminium does not react with it. Can anyone give me the reason for this? Not even a single one. Mamta, Anjanashree, Shivashankar. Okay. Okay. So it is because of the oxide layer that is being formed in the surface of the aluminium, right? So aluminium does not react with the concentrated HNO3 due to the formation of a protective oxide layer. So this is the aluminium block. So when it is kept in the atmosphere, the oxygen which is present in the atmosphere, it forms the protective oxide layer over that metal, so that when it is put inside the concentrated nitric acid solution, it will not react with it. Okay, so this is about it. Now we will go with the next topic of group 13, that is anomalous behavior of boron. So I already told you that anomalous means the unique nature. So the unique behavior of boron we will discuss. The unique behavior of boron is due to its small size, okay, and high electronegativity and the absence of d orbital. Okay. So boron is very small in size. On moving down the group, size increases, right? Boron is extremely small in size. So that is one of the unique nature of boron. So because of its small size, it can able to form strong covalent bond with the other elements. Okay. Whereas other elements of this group 13, like from aluminium till thallium, they will form ionic compound mostly. But because of its small size, boron is able to form a strong covalent bond with the other elements. Okay, and because of the high electronegativity, when size increases on moving down the group, electronegativity decreases, right? So electronegativity decreases means boron is the highest electronegative element in its group. So that is the second reason. And the third reason is the absence of d orbital. So boron belongs to second period. Second period means it has only s orbital and p orbital. Okay, so no d orbitals are present for boron. But for aluminium, gallium, indium, and thallium, we have d orbitals. Okay, if there are d orbitals, some electrons from outside, they can come and form the bond with the element which has d orbital. So that is absent in case of boron. So that is one of the reason for the unique behavior of boron. Okay, but some dissimilarities with the rest members of the group is there for boron. And coming to group 14, so these are the group 14 elements. Boron is diagonally related with the silicon. So there is a diagonal relationship for boron with silicon. Okay, so relationship in the sense, if we take size factor, more or less boron and silicon, they will have similar size and they will have similar electronegativity values. So like that, some similarities are present for boron with silicon. Okay, so diagonal relationship is between boron and silicon. So this is what you have to keep in mind. The three reasons for the unique nature of boron and the diagonal relationship with silicon. Got it? So now let us see some dissimilarities with aluminium. So we will see about the boron and aluminium, the dissimilarities with aluminium, boron with aluminium. So now boron is a non-metal. The only non-metal in the group 13 is boron, right? And aluminium is a metal. Boron shows allotropism. So allotropism means you can see. So there, all the atoms will be same, but due to the different structural arrangement, they will give different compounds. Okay, so kind of isomer B8, B10, and B12. So boron shows this kind of allotropism. Like carbon has allotropism, right? Carbon has three allotropes, right? One is graphite, and the other one is diamond, and the other one is fullerene. So in graphite, all the carbon atoms will be in the hexagonal form and they form a sheet-like structure. Whereas in case of diamond, they all get arranged in a tetrahedral manner and they are very hard. Okay, so like that, here also boron forms three allotropes of these three formula, and aluminium does not show any allotrope. Okay, so there is no allotropism for aluminium. And coming to the third point of boron, boron has very high melting point. You see, it is around 2200 degrees Celsius. It's very high, right? So very, very high melting point. But aluminium, it is moderate, just 660 degrees Celsius. Very low melting point compared to boron. And coming to the covalency, the maximum number of covalent bond that can be formed by the boron is 4. It doesn't have d orbital, right? So it has the outermost electrons. They will be in 2s and 2p. So electronic configuration for boron is 1s2, 2s2, 2p1, right? So in 2s it has 2 electron, and in 2p it has 1 electron. So totally it has 1 2s orbital and 3 2p orbital. So totally 4 orbitals only is there. So it can form only 4 bonds. Maximum is only 4. And coming to aluminium, aluminium has empty d orbitals. There will not be electrons, but aluminium belongs to third period. Since aluminium is a third period element, it has s orbital, p orbital, as well as d orbital. D orbitals are there. 3d orbitals will be there, but it will be empty. Okay. So in that empty orbital, elements from outside come with its electron and forms the bond with aluminium. So the aluminium can extend its covalency to 6. Maximum covalency for aluminium is 6. Okay. Now I will go with the fifth point. It forms stable hydrates. Boron forms stable hydrates like BH3, B2H6, all these hydrates. B2H6 is called as diborane, which has a banana shaped kind of structure. So these hydrates, when boron reacts with hydrogen, it forms hydrates, and those hydrates are stable. Okay, but aluminium hydrates are unstable. They form very unstable hydrates. And boron forms only covalent compound, as I've already told you in the previous slide. Because of its very small size, boron can form only covalent compounds. But aluminium forms covalent compound as well as ionic compound. Okay, so these are the very important 6 dissimilarities that boron and aluminium has among them. Okay, so do any of you have any doubt in this? Is this clear to all of you? All the points? All the concepts? Shall we go with the next slide? Yes or no? Is everything clear to all? Am I audible? Yes? Okay. Thank you so much, Anjanasri. Just give me a moment. Okay. Let us go with the diagonal relationship with silicon. As I have already told you, some of the properties are similar for boron with silicon, right? The first property is both are non-metal. Both boron and silicon, they are non-metals, and both have very, very high melting point. Both have very high melting point. And the oxides of both the elements, that is B2O3 and SiO2, the oxides of boron and silicon, both are acidic in nature. Both are acidic in nature. Like in this reaction, you see, when B2O3 is treated with sodium hydroxide is a base. Sodium hydroxide is a base. If this is a base, and obviously B2O3 should be an acid, right? Only base reacts with acid. So they form sodium borate and H2O. They form a salt with the release of H2O. So in the same manner, silicon dioxide, SiO2, also reacts with sodium hydroxide to give a salt. So in this reaction, SiO2 is acting as an acid. So both the oxides of boron and silicon, they are acidic in nature. Okay. And coming to the halides of both the elements, halides means fluorine, chlorine, bromine, and iodine, right? So when boron and silicon reacts with these halogens, they form halides. So the halides of both boron and silicon, they are hydrolyzed. Hydrolyzed means the halides, they will react with water to form the corresponding acids. You see here in the reaction. So I have taken boron trichloride. Okay, boron trichloride. So boron trichloride, when it is treated with water, when it is hydrolyzed with water, it forms H3BO3. So H3BO3 is a boric acid. Okay, it forms acid, and 3 hydrochloric acid, they are also coming out. They form corresponding acids. And when silicon tetrachloride, when silicon tetrachloride is treated with water, it also forms the silicic acid and HCl. Okay, so both the boron and silicon chlorides, they are producing the corresponding acids when they are hydrolyzed. Okay, and both forms carbides also. Carbides means the compound with carbon. Okay, B4C and SiC. So these are the boron carbide and silicon carbide. So both forms carbides, which are very, very hard. Both the carbides are very hard in nature. Got it? So these are the similarities with boron and silicon. Got it? First is about the metallic nature. Second is about the melting point. Third is about acidity. Fourth is about the hydrolysis of the halides of boron and silicon. And fourth is the carbides and hardness. Okay. So I hope this is clear to all of you. The reactions that are here with you on the screen, they are very, very important. Just have a look in it, because they may ask you to find out the product by giving the reactant. Okay, what type of acid will be formed when B2O3 reacts with NaOH. So in the given reaction, SiO2 acts as dash. So whether it is acting as an acid or base, you have to select. Okay, so that type of question you can expect from this. So this is about the thing. Now we will summarize the group 13 part. So yesterday we have discussed the atomic size, and this was the trend we have studied. And for ionization energy and for electronegativity, these are the trends that you have to study. Okay. And coming to the nature of oxides, as I already told you, B2O3 is acidic, the next two is amphoteric, and the last two is basic. Okay. And coming to the acidic nature of boron trihalides, BF3 is less acidic and BI3 is more acidic. So all these things we have discussed yesterday. Okay, this is just a summary of it. And coming to group 13, chemical properties. When group 13 elements reacts with air, they form oxides of E2O3 formula and nitrates of EN formula. Okay. And when they are hydrolyzed, when nitrates are hydrolyzed, they are forming hydroxides with the evolution of NH3 gas. And when group 13 elements reacts with water, that is steam, in the gaseous form of water, they also produce the oxides with the evolution of hydrogen gas. And when it is treated with sodium hydroxide, it forms hydrogen gas, and a salt it forms. And when it is treated with an acid, it forms a salt with the evolution of hydrogen gas. And when it is treated with carbon, it forms carbide, Al4C3 carbide it forms. And when this is treated with water, it forms hydroxides. And when it reacts with halogen, it forms halides of type EX3. And when this EX3 like BCl3, AlCl3, when it is treated with water, it forms again the hydroxides. Okay. So this is the general chemical property summary of group 13 elements. Okay. So you don't have to worry about the detailed chemical reactions of it. Okay. You just need to study the reaction with air. Okay. This product you have to study, and this reaction with acid you have to study, and the reaction with halogen you have to study. Okay, these are very important part. Now next we will study the carbon family. So do any of you have any doubt in the boron family? If you're having any doubt, you can ask me now. I'll give you some seconds. If everything is clear to you, just give me a thumbs up or type yes in the chat box. We can move on to carbon family. Okay. Okay. Thank you so much, Anjanasri. Yes. Thank you, students. Thank you. Yeah, let's start with the carbon family now. So now in carbon family also, we are going to see the introduction to carbon family and the trends in general properties of group 14 elements, and the properties of group 14 elements, chemical properties, and last is the anomalous behavior of carbon. Okay. Yeah, sorry, Anjanastri. Yes, I'll repeat it. The carbon family members are carbon, silicon, germanium, tin, lead, and flerovium. Carbon is the 17th most abundant element by mass in the earth crust, and it is existing in coal, graphite, and in diamond. I told you, no, in graphite it will be there in sheet-like structure, and in diamond it is tetrahedral in geometry. So in all these elements we can find the carbon, and it has two stable isotopes. There are three isotopes for carbon, but among those three, what are isotopes? Isotopes are the elements whose atomic number is same but mass number is different. Okay, the atomic number for these two carbon, they are same. What is atomic number of carbon? It is 6, right? But you see the mass number. In one element it is 12, and in the other element it is 13. And in the third element it is 14. So 12, 13, these two are stable, and 14 is unstable. So that's why it is radioactive. Radioactive, most of the radioactive compounds are unstable. So we cannot able to study the chemistry of all the unstable compounds. So in the same way, carbon 14 is unstable with a half-life of 5,770 years, and it is used for carbon dating. So that is out of your thing, okay? Carbon dating is some other, it is a separate concept. So this is the general introduction of group 14, that is carbon family, about the carbon. Now next we will study the introduction of silicon. Silicon is the second most abundant element by mass in the earth crust. It is there in silica sand, and it is present in the form of silicates. Okay, so in these two forms we can see the silicon, And coming to the third element, that is germanium, it exists only in very trace amount, very, very small amount. Okay. And coming to the fourth element. So who is the fourth element? Tin and lead, right? The formula for tin is Sn and for formula for lead is Pb. So these two elements, they occur in the form of cassiterite and lead is occurring in the form of galena. So cassiterite formula is SnO2. So in the form of oxide, tin is existing and lead is existing in the form of sulfide. Okay, PbS. PbS is galena. Okay. So these two elements are existing in these oxides and sulfides form. And coming to the last element, which is radioactive, that is flerovium. It is synthetically prepared radioactive element. So this is very important. It is synthetically prepared radioactive element. So we are preparing this element in the lab. So that is called a synthetically prepared. It is not occurring naturally. It is not a naturally occurring element. Okay, it is synthetically prepared. That too, it is unstable, radioactive element. So this is about the occurrence of all these group 14 elements. Okay. Now next we will jump to the electronic configuration of group 14. So these are the group 14 elements: carbon, silicon, germanium, tin and lead, flerovium. The general electronic configuration for group 14 is Ns2 and Np2. Okay, this is a general electronic configuration. And now since carbon belongs to the second period, the configuration would be 2s2, 2p2. And for silicon, 3s2, 3p2. And for germanium, 4s2, 4p2. But in between 4s and 4p, 3d orbitals will also be present. That is also fully filled. Okay, so 4s2, 3d10 and 4p2. Then coming to tin, 5s2, 4d10 and 5p2. Okay, coming to lead, we have both 5d orbital as well as 4f orbital. So 6s2, 6p2 is there, and in between that 4f14 and 5d10 is also present. Now in the same way, flerovium also contains f orbital and d orbital, 7s2, 5f14, 6d10 and 7p2. So only two f orbitals are there and 4 d orbitals would be there. Okay. So these are the things you have to keep in mind while picking out the electronic configuration of the corresponding element. And the last element, as I already told you, flerovium, it is radioactive in nature. Okay, radioactive. The only radioactive element in carbon group is flerovium. Got it? So any doubts so far? Shall we go with the trends and general properties of group 14 elements? Say yes or no. I'm not able to switch on my camera. Sorry for it. I don't have power here in my place. So that's why. Yeah, Hashira, when did you join? Good afternoon. Now only I can able to see you. Okay, good. Okay, fine, students. So we will move on with the trends and general properties of group 14 elements. Yeah, good afternoon, good afternoon. Try to join on time, okay? So we have class at 3 o'clock, right? I'm starting the class just after 5 minutes only. Since you guys are joining very late, I'm starting the class after like around 3, 7, 3, 8 only. I'm starting the class. Try to join on time so that we can cover the portions easily and we can solve some questions in the class. Fine. So let's start with the trends in the general properties. So the first property is atomic size. Trend in the atomic size. Same as that of the group 13. Here also we are going to see about the atomic size first. So the same graph. This is carbon, silicon, germanium, tin and lead. So in boron group, we have seen some exception, right? Among aluminium and gallium, there we had some exception, right? So here, no such exceptions are there. You see the values, it is going from 77 till 146 picometer. So there is an increase. There is a considerable increase in the covalent radius from carbon to silicon. But from silicon to lead, so the increase is there. It is what to say, only the difference is very less compared to carbon and silicon difference. The difference between silicon and germanium and tin, if you see, they are considerably very less. So tin and from silicon to lead, a small increase in the radius is only observed. Okay, it is due to the poor screening of d electrons and f electrons. The same concept which we have seen in the boron family thing. Okay, so increase is very less due to the poor shielding of these d and f electrons. Now the trend of this group 14 elements for sizes: carbon, silicon, germanium, tin and lead. So there is no exception here. Just memorize the elements of group 14 and pick out the trend in that order. Okay, on moving down the group, size increases. That's all. So if they ask you the reason for this small increase in the radius, you have to tell this poor shielding of D and F subshell. That's all. Okay. No other exception or no other point you have to keep in mind in this. Now we will go with the second property, that is ionization energy. As I've already told you, ionization energy is the energy required to remove the outermost electron from an isolated gaseous atom. Okay. So let us see the trend of it. Atomic size is inversely proportional to ionization energy. So their atomic size increases from carbon till lead. Now ionization energy will decrease from carbon to lead. So for carbon, you see the energy value, it is 1086 kilojoule per mole, and it is decreasing, keeping on decreasing. Okay, the decrease is very large from carbon to silicon, and after that it is only a gradual decrease. Okay, so the first ionization enthalpy, that is delta H1 of group 14 members, is higher than the corresponding members of group 13. So let me take boron and carbon. Okay, boron is group 13 and carbon belongs to group 14. So group 14 will have the highest ionization energy value because across the period size decreases. Across the period size decreases. So ionization energy value should increase. So when you compare boron and carbon, carbon would obviously have the highest ionization energy value. Okay, that is this first point. And coming to the last two members, that is tin and lead, they are more or less they are having the similar ionization energy value. Okay, this is 708, tin is 708 and lead is 715. So it is due to the inert pair effect. Already taught you know the inert pair effect. It is due to that reason. The reluctance of s electron to take part in bonding is called as inert pair effect. So due to that effect, the charge which is present inside the nucleus, that is effective nuclear charge, increases. So lead is having the highest ionization energy value compared to tin. So the regular order should be lead should be lesser in the value, right? Lead should have the lowest value compared to tin. But here a small increase is observed. So this exception is due to the inert pair effect. Okay. Now the trend is tin, first carbon, then silicon, germanium. And you have to just interchange the place of tin and lead. That's all. Just interchange these two elements place. Okay. So here is tin and here is it is lead. Just interchange these two elements place. You will get the order and or the trend for ionization enthalpy. Okay. So now we will move on with the electronegativity. So the tendency to attract the shared pair of electrons towards itself is called as electronegativity, right? Now for electronegativity, the trend is like this. So the trend that is being observed, atomic size is again inversely proportional to electronegativity, right? So the carbon is having the electronegative value of 2.5, then silicon 1.8, it decreases. Germanium, same as that of silicon, and tin, same, and lead is 1.9. Okay. So from silicon till tin, electronegativity values are almost same, right? So they're almost around this 1.8 and 1.9. And also for the last two elements, for tin and lead, you see there is an increase for tin and lead like ionization energy. Again, it is due to the same reason, due to inert pair effect. Okay, this exception is observed due to the inert pair effect. So the trend is like this. First carbon 2.5, then lead 1.9, then silicon, germanium, tin. All these three are approximately having the same value. So this is the correct trend that is being observed for electronegativity of group 14. Okay, so these three trends keep in mind. Now we will study the properties of group 14, the physical property and chemical properties of group 14 elements. Okay, so do any of you have any doubt from the three general properties that we have discussed? Atomic size, ionization energy, and electronegativity. Is everything clear? All of you, just respond me. Okay. Okay. Thank you so much, students. Now coming to the properties of group 14 elements. The first is about the physical property. All the members of group 14 are solids. From carbon, silicon, germanium, tin, lead, all are solids. Okay. Coming to the metallic nature, carbon and silicon are metals. And germanium is a metalloid. Metalloid means semi-metal. Okay. And tin and the lead, these two elements are metals. So the metallic nature increases on moving down the group. When you are moving from carbon to lead, the metallic nature increases from non-metallic nature to metallic nature. Okay, the only semi-metal or the only metalloid in group 14 is germanium. Okay. Now coming to the melting point and boiling point of group 14, they are very, very high. Melting point and boiling point of group 14 elements are much higher than those of the corresponding elements of group 13. I'll show you the graph with atomic number and temperature. You see the blue color dot, this represents a melting point. So melting point, it is decreasing from carbon till lead. Okay, temperature is decreasing and boiling point is also decreasing. But you see the value, carbon is having the melting point of 4373. This is actually very high, extremely high, right? And the boiling point also, it is extremely very high compared to group 13 elements. So this is the comparison you have to study between these two groups. Both the melting and boiling points are high for this. Now coming to the oxidation state and the chemical reactivity of this group for carbon group. Coming to talking about carbon, carbon has the very highest ionization energy. Since its size is very small, ionization energy is very high for carbon. So what does it do? It always forms covalent bond. Because of its highest ionization energy, it forms only covalent bond in +4 oxidation state. So the valency of carbon is 4, right? So it always tries to form the covalent bond. So it will not give its electron mostly. So it always tries to share its electron and forms the covalent bond. And in some cases, it forms +4 oxidation state. Okay. And the higher members show, higher members means tin, lead. So those elements, they show oxidation state of +2 due to the poor screening by 4f and 5d subshell electron, which is called as inert pair effect, which we have already discussed in boron group. Okay. So these 4f electrons and 5d electrons, they will not shield. If this is the nucleus, this is shell number 1, shell 2, shell 3, shell 4 and shell 5, right? And shell 6. So in sixth shell only, the electrons of tin and lead would be there. The 5s electrons of tin and lead would be there. Okay. In fifth shell, if we will have 5d electron, and fourth shell we have 4f electron. So the electrons which is present in the 4f and 5d, they will not shield properly. So the electron which is there in 6s2 and 6p1, so these electrons, so they mainly the s electron which is there in the sixth shell, because of the poor shielding of 4f and 5d, they will come and get attracted towards the nucleus. So they cannot able to take part in the bonding. And the electrons which are two electrons which are there in 6p orbital, only they can form the bond with the other element. So they can donate only 2 electrons. Tin and lead can donate only 2 electrons. So they cannot donate 4 electrons. So the +2 oxidation state is more stable for the higher members. Okay. Now +2 stability also you see. Lead-2+ is more stable. As I already told you, lower oxidation states are more stable on moving down the group. So since lead is the last element, it is stable at in that +2 state, more stable, and next comes the tin and next comes our germanium. Okay. Now germanium 2+ is less stable compared to 4+. So if germanium 2+ wants to become 4+, what it has to do? It has to lose 2 electrons. Already it has lost 2 electrons and it is existing in the form of germanium 2+. But this is less stable compared to 4+. So what does it do? It again loses its 2 electron and it becomes 4+ and it becomes stable. So if an element is losing its electrons, then we call that particular compound as reducing agent, right? So germanium 2+ is reducing agent. Germanium 2+ compounds are good reducing agents. Okay. But lead 2+, if you see, lead 2+ is more stable because the lower oxidation states are more stable for higher members. So lead 2+ is more stable compared to 4+. Okay, lead 2+ is more stable compared to 4+. So if lead 4+ wants to become 2+, it has to gain 2 electron. It has to gain 2 electron. When it gains 2 electron, 4+ becomes 2+, right? So the compound which is gaining the electron are called as oxidizing agent. All the lead 4+ compounds, they will act as a strong oxidizing agent. Okay, these are very important. Just have a look on it. If you're having any doubt, you just ask me. Okay. Is this part clear to all of you? Shall I go with the next slide? Just let me know in the chat box or give me a thumbs up. Yes. Okay. Carbon cannot exceed its covalency more than 4. This is one of the very important point we have to keep in mind. Yes. Okay, Shamir. So the maximum covalency is 4 for carbon because of the same reason that boron had one reason, no? That boron doesn't have a d orbital. So the maximum covalency for boron is 4. Here, carbon cannot exceed its covalency more than it can form only 4 bonds. But when you see for silicon, germanium, tin, they can expand their valency. You see here, silicon is forming 6 bond with fluorine and germanium is forming 6 bond with chlorine, and tin is having 6 bonds, OH groups inside it. So these silicon, germanium, tin, they undergo hydrolysis, or their halides undergo hydrolysis, and they have the tendency to form complexes like this. Like this means they can able to form 6 bonds. They can expand their valency from 4 to 6 because of the presence of empty d orbitals. Okay. And in all these compounds, in all these complexes, if you see, the hybridization of the silicon, germanium and tin are sp3d2. sp3d2. If the geometry is, if the hybridization is sp3d2, then the geometry is octahedral. Okay. Let me draw for silicon. If silicon is like this, it will form bond with 6 fluorine like this, in which 4 fluorines are there in the square plane, one above and another below. So this is a octahedral. Okay, it has 8 faces, so it is an octahedral. I will discuss all these things in the chemical bonding lesson or in class 12 with you in detail. Okay, so now for now, You just keep in mind that if the hybridization is sp3d2, geometry is octahedral. That's all. Okay. Now next we will go with the properties of group 14 elements. Some of the general chemical properties we will discuss. So any doubt? Any doubt from the previous slide, students? Have you all noted? Noted it down? Yes or no? No? No doubt, or you did not noted it down? Yes. Okay. Okay, let's see the properties of group 14. No doubt. Okay, okay. Yeah, the first property is the reaction with oxygen. So therefore, boron group we have studied. No, first was the reaction with the air. Here is the reaction with oxygen. So all the carbon group elements, they react with oxygen and they form two different types of oxides. One is of formula EO, that is monoxide, and the other one is EO2, dioxide. Okay, so if carbon is reacting with O2, it forms carbon monoxide as well as carbon dioxide. So like in the same way, silicon, germanium, tin, lead, everything will form. So talking about the monoxides alone of the elements of group 14, these are the elements, monoxides of these elements. And among these 5 monoxides, carbon monoxide is neutral. It is one of the neutral compound. And silicon and germanium monoxides are acidic. And the last two, they are amphoteric. Okay. Just take it down. Take it down. All these are very important. And coming to the dioxides, the first 3 dioxides, carbon dioxide, silicon dioxide, germanium dioxide, all these 3 oxides are acidic. Last two is amphoteric. Okay. Very important. This acidic nature, you should know. Which among the following is acidic in nature? Which among the following is amphoteric in nature? Which among the following is neutral in nature? Or which is the neutral oxide among the given compound? So they will ask questions like this. So if you know the order and the acidity of all the oxides, you can pick out the answer easily without getting confused. Okay. Fine. So next we will go with the second reaction, that is reaction with halogen. Shall I move on with the halogen reaction? Did you all take it down? Okay. Good. Good, Mamta. Yes. Now is the reaction with halogen. Yeah, good students, good. So now halogens are denoted or represented by the letter X, and those halogens are fluorine, chlorine, bromine, and iodine. Now, when, yeah, yes, Ashira, good. When the element reacts with halogen, again here they form two different types of halide. One is a formula EX2, which is called dihalide, but carbon cannot form dihalide. Carbon can form only tetrahalide. Tetrahalide means a formula EX4. Carbon can form tetrahalide, but lead and lead tetrabromide and lead tetraiodide, that is not there. Okay, why it is not there? Can anyone tell me? Why lead cannot form 4 bonds with halogen? Why there is an exception for lead alone in this case? Any idea? Why lead is not forming tetrahalides? Why lead is not forming tetrahalide, but it is able to form dihalide? Any idea? Just think of the previous concept that I have discussed with you today. Just think of it. No idea? Not even a single student is listening my class. Huh? It is due to the stability of lower oxidation state. I told you, right? Lead is stable only at +2 state. But here in these two compounds, lead is stable. Lead is in +4 oxidation state. It is bonded with 4 halogen. So it is in +4 oxidation state. So it is not stable. So that's why Tetrahalides are not possible and they are not able to form when the elements, when lead reacts with halogen. Okay. So they form only PbBr2 and PbI2. Coming to the tetrahalides, EX4, the tetrahalides are covalent in nature except tin and lead again. They are not stable. So they are not covalent in nature. And this is the structure of the tetrahalide. They form 4 covalent bond and the hybridization is of the central element is sp3. So the geometry is tetrahedral. Geometry is tetrahedral. The thermal stability of all the tetrahalides, they decreases on moving down the group. Tetrahalide means CX4, SiX4, germanium X4. So all these tetrahalides, stability is decreasing. So the carbon tetrahalide is more stable compared to the other element, compared to next and next. Okay. But if the central element is same, if the central element is carbon and if I am changing the halogen, like CF4, CCl4, CBr4, Ci4, CF4 is more stable. CF4 stability is more stable. So all these order you have to study. Coming to the stability of dihalides, they increases down the group. So I already told you, no, lead is stable only at +2 oxidation state. And here it is in +4. That's why it is the least stable and here it is the most stable. Lower oxidation state elements are more stable for higher members. So this is about the reaction with halogen. And when these halides, when these EX2, EX4, when these halides undergoes hydrolysis, what is going to happen? That we will see here. Except carbon halide, all other halides are easily hydrolyzed. All other halides are can easily react with water and get hydrolyzed. Suppose if I am taking SiCl4, so this is the silicon tetrachloride. When it reacts with water, when 2 molecules of water comes in contact with it, those water molecule will come and interact with the silicon. How it is interacting? Silicon is having empty d orbital. So the lone pair of electrons which is there on the oxygen, they will come and form the bond with the silicon. Okay, they will form the bond with the silicon and hydrogen bonding is also occurring. And the second molecule is also interacting and the second hydrogen bond is formed between H and Cl. And it leads to HCl. HCl will come out. HCl will come out and we will have OH, 2OH replacing the 2HCl. Okay. And now the third water molecule, fourth water molecule will also come and they will also form the bond with silicon and the 2 chlorines will go out with the hydrogen as HCl. So totally how many HCl is going out? 4 HCl is going out and all the 4 Cl atoms are replaced by OH group. So SiCl4 is getting converted to SiOH 4 times. And this compound is called as silicic acid. This is called as silicic acid. So all the carbon, except carbon halides, all other halides are easily hydrolyzed by the water to form the hydroxides. And those hydroxides are acidic in nature. Okay. So this is about the reaction with halogen. Okay, it's already time. Then the next is the reaction with water that we will discuss in the next class. Tomorrow we will discuss. Okay. So do any of you have any doubt from the anomalous behavior of boron or from the introduction of carbon and the general properties, atomic size, ionization energy, electronegativity, those trends and the reactions of carbon group members? No, madam. Everything is clear, madam. Okay. Okay, Hashira. Okay, then students, thank you all for listening the class. So we will meet in the next class. Okay. Thank you so much. Bye-bye. Thank you. Thank you.